start at 3:15, so we can be about an hour to an hour and a half for review and get you out of here. But thank you for coming. If you're still coming in, please do come in and find a seat. I do still have a few copies of the actual review questions. They're on C-Tools, but in case you forgot to bring your copy. And if you would give me your ears, I will run through a couple of announcements. So you still have labs this week. Labs will be some review. Hey guys, you do need to have a start, okay? So in labs this week, you'll do an in-lab project on hypothesis testing. So another review of H0, HA for proportions. There will be some review questions, little in-lab review they'll do with you too. Make sure you get that pre-lab number 4 done before you go to lab. Lecture. On your list of things to do this week, we put together some lecture review questions. Please print out a copy of those. That's just 2 pages. We'll do a couple on Monday, Tuesday, and a couple on Wednesday, Thursday. So bring those with to lecture in all classes. When you come on Thursday night, you don't really have to bring a whole lot with you. Hey guys, I know it's going to be hard, but big room, lots of people. Do need to bring your ID because your GSI might not be in that room. Most of the time they are, but sometimes we have to pull them to a different room to cover the larger rooms versus the smaller ones. Bring your ID, bring things to write with. Backup one, not just one that might run out of ink or lead. Bring your calculator. You do not need to bring your formula card or yellow card. That'll be provided for you. Doors will be closed until we're ready and got the room set up. We'll have the yellow cards laid out. And you'll be led in the room about 5:45, 10 to 6 maybe, to get your seat. You'll be asked to put your bags, your books, purses, and so on along the wall. You can't take them to your seat and put them in front of you. It causes tripping, and we don't want any of that material sitting right there. So you're going to ask me to put it in the front of the wall. Makes it easier for getting in and out. As students leave, because they're finished, they are able to leave. You bring your exam to the front, you sign in, and you grab your things and you go. All right. Hopefully you know where you're going to be going. Here is your exam 1 info again. It is at night. It's supposed to start at 6 o'clock. Usually we start anywhere between 6:02 and 6:05. And you still get your hour and a half because we have the rooms past 7:30. Is there a question? I haven't seen this before. Should be okay. Page 93 is the magical page in your lecture notes for where the material stopped. We're past 93 in lecture. That's new material that wouldn't be formally tested. Some ideas are still there, but not formal. All right, here's what I plan to do for the review. My first 3 slides are just an overview. Sit back and listen. You do not have to write it all out. I will post those 3 slides in full right after the review. Just kind of putting all the terms in our head, how they kind of fit together. And then after that, we turn to the questions. And we'll go through them, maybe some tangent questions along the way. And if you have questions along the way, you may raise your hand. And I'll try to address them too. We've got quite a few people that are still coming in. There are seats available in between. You're welcome to still come in and get a seat so you can sit rather than stand or sit on the floor. So if you have a seat next to you, maybe you can let people know that. If you'd like to have a seat, you're welcome to do so. There are still some available. All right. Come on down if you'd like and try to find a seat. So as I said, these first few slides, just an overview. Let's get some terms from chapters 1 through part of chapter 12 in our head. We began the class looking at data. We talked about different types of data. And they were of what two types? What did we use to classify data at the beginning in Chapter 2? Either categorical or quantitative. That was our first way of distinguishing between those two types of data. And depending on what type the data are, it allowed us to do different kinds of summaries. On the categorical side, and again, these will go up for you with the full slide, so you don't have to write them down if you don't want, you can just listen. Are we comfortable with frequency tables? That's just doing the counting for the different categories, how many or what proportion. Then we had bar charts and we had pie charts in our notes. Didn't see a lot of pie charts, we weren't making them ourselves anyway, but bar charts were there. And sometimes it's easy to get a bar chart confused with a histogram. But a bar chart is for categorical data. Often there should be a gap in between the bars because they are just separate categories. And a bar chart is what you cannot comment about in terms of shape, because those categories could be reordered in a different way and make it look different in terms of a shape aspect. So we only talk about there's more of one category versus another. Twice as many people said yes versus no. We compare the heights of the bars. What do we have on the quantitative side? Let's say the first real graph we looked at that did show the shape for the distribution of some quantitative variable. That was what? Histogram. Histogram's the primary one that shows shape. We also looked at box plots as a 5-number summary for a quantitative variable. Time plots were useful only if your data was gathered over time or some ordering. In fact, that's usually a graph we should look at first to make sure that the data gathered over time could be summarized together into a histogram, or possibly calculate a mean or some kind of numerical summary. And then QQ plots were introduced to specifically look for what aspect in the distribution, to see if it is a bell-shaped distribution or a normal distribution in particular. So QQ plots do help us to decide about shape, specifically if it's bell-shaped or not. And of course, the histograms allow us to comment on shape, spread, proximate center, things like that. What was useful about box plots? What did box plots sometimes point out for us? Outliers. Had a nice rule to truly identify a point as being an outlier, so you could draw attention to it. Any outlier that's there, though, is still part of your data set. And even though it's an outlier doesn't mean you ignore it. You actually have to still use it if you were calculating the range or pointing out the largest or the smallest value in your data set. Good. Box plots, though, are not so good at showing you the shape. They can't prove that something is symmetric or bell-shaped or anything like that, but they can be looked at along with the histogram. All right, now on the quantitative side, we went to means and medians. We calculated the 5-number summary and the IQR. We talked about the standard deviation. We had a nice interpretation of the standard deviation. And we even talked about the thing called the empirical rule, which you're still using. That empirical rule was what? 68, 95, 99.7. For what kind of distribution does that apply? For a bell-shaped, a normal curve. And that's why we even talk about if you go out 2 standard deviations, about 95%, we're still letting you use 2 for your Z star value when you make a confidence interval. Because that's where it's coming from, 2 standard deviations each way. All right, and then we talked about maybe our sort of one statistic called a sample mean, X bar. We're going to start revisiting that sample mean as another statistic to estimate the population mean coming up this week and next. It's not on your exam, but it certainly will be on exam 2. On the categorical side, that's where we counted up how many are in each category. Lots of counting going on. Sometimes it was either yeses or nos, successes or failures. We counted up how many actually were successes in our sample. In fact, when we had this variable being the number of successes in your sample, it had a nice model that we use sometimes to even do a small sample test of hypotheses. And what model was that again? Binomial. Binomial is the model for the number of successes. And then sometimes we converted that to the proportion. So here were a couple of quantities on our sample that we would summarize categorical data with. All right. Now, chapters 3 and 4 did a little bit about where did the data come from? How did we gather the data? What were the 2 main types of studies? It's either observational or experimental or experiment. So we had observational studies and experiment. Know the difference between them. In an experiment, you have the active imposition of the treatments on the subjects, if you will. You're modifying and changing those different factors. Observational side, you're simply recording. Didn't do anything specific to the things that you're measuring except to observe what they had. All right, in either case, we had variables. And we had those variables have a role that they played. So data can be categorical or quantitative. These variables we're measuring can either play the role of a response or an explanatory, or sometimes you have those variables that are confounding, that could influence the results, the response, and you need to record them so you can control for those confounding variables. We also had some different biases. What were those 3 types of biases? We had selection bias, how you gather the data. You had response bias, or if you didn't respond. Exactly. Those are the 3 main types. Placebo effect, for example, is a type of response bias that can happen, because if you give someone a treatment, they tend to give you that indicated outcome that you're looking for. That's a placebo effect bias or response bias. And we have different means of trying to control for those too, especially on the experiment side. Because on the experiment side, we do randomization. We set up a control group if we can. We give that control group a placebo treatment if we are able to, so we can counteract those different biases. And do you know the term blinding and what that means? You can have single blinding or double blinding. Single blinding is typically the response, or the person giving the responses doesn't know which treatment they had. But double blinding is the person that's recording or measuring the responses also does not know which treatment that person had. So they aren't biased in what they're writing down. On the observational side, talked about sample surveys a lot there. That's where we got our first confidence interval. We talked about trying to estimate a population proportion with certain level of confidence, and you learned your very first margin of error there. It was actually a 95% conservative approximate margin of error. What was that nice, easy formula? 1 over square root of n. That will still work Thursday night if I ask you to give me a 95% conservative confidence interval. You can use 1 over square root of n. It comes from your formula for the conservative interval when you put z star of 2 in there. It's exactly what you would get. All right. We now started to think about, we're going to be using the data, the summaries of our samples, to try to learn something about the population. And we know that when we do that, there's uncertainty. We're not going to get the right answer every time. We wanted to measure that uncertainty, and that was through Chapter 7 material. We started measuring outcomes and how likely they would be to occur through probability. In fact, your p-value that you calculate all the time is a probability. Probability of seeing what you got through your data, or more extreme, under the H0, theory being true. So when we combine probability with our data, instead of just calling them variables, we call them random variables. And now instead of saying they're categorical data or quantitative, we had to talk about whether the random variable was of one type or another for its modeling. And what were the 2 main types of random variables? Discrete or continuous. And that dictated what kind of model we have to describe the values for that random variable and how often they occur. All right, so what were some of the ways we did discrete? We had a probability table sometimes. Remember the number of toys played with in that psychology experiment? The table would give us the values of x and their probabilities. We showed you how to find the mean and the standard deviation. Those formulas are on your yellow card. And then we had a specific family of discrete variables called the binomial. Now you've seen a lot, and I've had students ask, even an email, when you define a distribution, you want to make sure you give me the full model. So if I say binomial, I'm going to ask you, which binomial? Give me the n and give me the p. So then I know which binomial model you're actually talking about or using. Indexed by that n and p. And that was the model for the number of successes in your sample. Now, we didn't have you calculate all the probabilities and put it together in a table. We just used that one formula from your yellow card that gives you the binomial probabilities for any particular value you want to find, how likely it is to occur. And we had a nicer, easier formula for the mean and the standard deviation. So you want to be able to identify if it's a binomial situation. You read through that 1 or 2 sentence background, there should be an N and there should be a P. And you should be looking at how many people said yes, how many successes were there in the sample, how many patients responded favorably. Those are counting the number of successes. That's a binomial scenario. On the continuous side, what were some of those? We didn't have a table anymore. We didn't have discrete probabilities, but we had a curve. What was a curve called in general? It's called, what would you put on the y-axis if you were drawing any kind of curve? A density function, a density model. So we had density curves. We had curves that were skewed one way or the other, that were symmetric and bell-shaped. We had some that were uniform, and the bell curves coming back again too. So we talked about just a general density function, which has what property again? The total area under the curve is 1. So we use that often. If there's a piece missing and we've got the rest, we can figure it out. Uniform we can work with pretty easily on our own. We don't need a table of areas for that one, because you can find the areas under a rectangle fairly easily. If this is a generic A and B, then how would you figure out what the height is? You have to take the distance, right? B minus A or 10 minus 0, whatever they are, and do 1 over that. Your general height would be 1 over however long your base is in a uniform. And then you've got that one value you need to find out areas. And then, of course, the normal family of densities we've used a lot. We have a lot of things that follow a bell curve. Heights, weights, different measurements, but also a lot of statistics that follow a bell curve. The first statistic we looked at was the binomial statistic when n was large. And then the p-hat statistic follows a normal model too if n is large. So we end up using the normal model a lot. But again, I'm giving you sort of the compact notation, and you've got to put in there the values so I know which curve you're talking about. All right? Good. Now, the couple statistics we calculated over on the discrete side was the count or the proportion. We'll be focusing on them in a couple of our review questions. We'll be testing theories about the true proportion using that sample proportion p-hat. And on the continuous side, the one main statistic that you're going to be introduced to this week in class is the sample mean, coming back again, and how well that is at estimating a population mean. You've calculated a sample mean before, but we're going to study it as a statistic in terms of its distribution coming up. All right, so there's a couple of the terms in mind. We're going to talk about confidence intervals and testing as we do some of the problems. But those were some of the big ideas from those first few chapters. We'll now move into the review questions, which will highlight confidence intervals, testing, modeling, all of these different kind of terms. So we'll turn to question number 1. And these were questions from a previous exam. I don't remember how many questions are on your exam. I think it's 9, maybe 10. It's spread out, though, over many pages, so you have lots of space. I never like to have 2 questions squished into one, if I can just spread them all out. Hey, this is 8 questions right here. We're going to go through them in an hour. You should be fine. I expect most to finish in an hour to an hour and 15 minutes. You have the full hour and a half if you need it and would like to use it to go back and check that question mark question. All right, what do you see in question number 1? We're looking at the number of new employees for 15 years at a company. And so they recorded how many were new employees for this year, how many new employees were hired for this next year. This is their quantitative response, and a histogram was made of these values. We're asked in part A to work out what proportion of the years that we're looking at here did they end up hiring 170 or more new employees. Now, usually your histogram is broken up into classes of equally sized. And unless it's dictated otherwise, most packages will always include the value on the left, so like 170 here, and it will go up to, but less than the value on the right. You have to have an idea of where does the 170 go. And most conventions for most packages are that the value on the left-hand side is included. The value on the right-hand side is that upper bound that you're not quite getting to. So we want 170 or more. 170 is really right here as a value. It's included in this particular class and also this last one. So how many years were there 170 to less than 190 new employees hired? What would that be? There were 5 years where that many employees were hired as new employees. And over that 15-year period, how many years did they hire a huge amount, 190 or more? That would be just 2. The height of the histogram tells you how many fell into that particular range of values. I want to know the proportion of years in which they hired 170 more. How many years did that correspond to? 7. Is 7 my answer? No, 7 out of how many years altogether? 15. If you're not sure, you can add up your values. Oops, that's a 3, 2, 2, and 1. You have a total of 15 observations, 15 years of data. Work with your histogram. If you have to read a number off and it's not quite as clear whether that really is a 5, it's pretty clear here, but if there was a different kind of scaling, show me what you're doing. And I'll have a little range of reasonable values that you'll pull off. So if it's 120 or 122 or 121, those might all be acceptable answers. I'd like to see 7 out of 15. That's good work. I can see the numerator and denominator are all given. If you added things up wrong and got 16 or something else, I could see where the data comes from, your numbers come from. Possibly give you some partial credit. 7 out of 15 works. That's a right answer. So does 0.467 if you convert it to decimal, or if you put 46.7%. That's okay too. All right. How about descriptors for this histogram? If we treat x as our variable, our random variable, that's quantitative, and look at this histogram, kind of smooth it out. What are some of the words that might be used to describe this histogram in terms of the distribution here? So we're not symmetric, right? Unimodal? Yep. I get people mixing up unimodal with uniform. Unimodal is one main mode or peak, not bimodal here. There's definitely some skewness. Which direction? You look at where the tail is pulled out. That's the direction of the skewness. Skewed to the left, not to the right, and of course not uniform either. Good. In a skewed to the left distribution, which value would you expect to be smaller, the mean or the median? Which one is the one that's sensitive to skewness and outliers? The mean. The mean is the one that tend to be pulled towards that tail where the skewness is going. So the mean would typically be a little smaller here than the median due to the skewed left shape. All right, now the data we have here is over 15 years, from 1995 to 2009. There is a better graph that we should have made right at the start before we do a histogram, before we talk about a mean or a median. And what graph would have been the first graph we should have made? Could simply call it a time plot. Some packages call it a sequence plot because you're plotting over the sequence or order of the data. So we made a time plot. How do you know it's a time plot? A time plot has what on the x-axis? Time. Time or order. This would be the year. So it would be 1995 all the way up to 2009. Where is your response variable? It's not the x-axis anymore like it was in the histogram. It's on the y-axis. This is your response, the number of new employees. And you will plot that data over the time. Now, if the histogram is okay to make, I hope I see here no pattern. If I saw a pattern in my time plot indicating an increasing trend or maybe increasing variability, well, then it would not be appropriate to even make a histogram. Because in order for me to make a histogram, I have to assume that data looks like a random sample from the population of all values for a number of new employees hired. And the only way to assume it's a random sample is if you have what for a random sample? Random sample means they're independent observations and identically distributed. And your time plot's checking for identically distributed, otherwise known as stable. That's what you're hoping you see in the time plot. If the observations are relatively stable, around a common value, a common mean, common amount of variability, then it's okay to summarize it with a histogram and or a mean and some other numerical summaries. All right, so your time plots are used to check for stability, to make sure you could combine that data into one set of observations to graph and further summarize. Good. There are ways of showing instability, either with a change in the mean, increasing trend or decreasing trend, increasing variability or decreasing variability, or sort of the trumpet type shape plots where you have an increasing variability in the response over time. Any of those cases, it would not be appropriate to make a histogram, not be appropriate to summarize with a mean or standard deviation, because the data's been coming from a bunch of populations that have changed over time. All right, question number 2. Let's turn to that one. Here we're looking at strength of wood, a project to study the physical properties of wood. So they take a bunch of wood of different types of species, aspen, birch, or maple. Then they have these different flakes of that type of wood that are made and fused together, bonded together. The flakes are either of size A or size B. And what they wanted to determine was, what combination gives you the strongest wood? Certain species type and a certain size of the flake, when put together, which one will be the strongest? Measuring strength. So what kind of study do I have here? Is it an observational study or an experiment? There aren't really subjects here, are there? I mean, there's not people, but you did take the different species of wood and you broke it up into pieces of different size and put them together to be of a certain combination of these two different treatments or factors. So it is a designed experiment. They didn't just find wood of certain species and just measure the strength and record these two different features, what species it is and the size of the flake. They actually formed those together. They imposed the treatments to form the piece of wood that they measured for strength. All right, so we need response variable, explanatory variable. There can be more than one. What's the main outcome of interest here? The response that they're interested in measuring and knowing how things affect it. The strength. Lots of studies have many different response variables, but this is the primary one we're looking at here. How about what they think will explain the strength or contribute to how strong it'll be? This type of wood, or they call it the species. Species of the wood, and what else? What's another explanatory variable here? The size, the flake size of flake. And there are 3 different species of wood. There are 2 sizes of flakes. So there are 6 different treatment combinations, if you will. And they'll probably have a few types of wood with these different sizes to be able to measure strength multiple times, having replication of those different treatment combinations. All right, response variable and explanatory variable. What do we fill in the blank with? When we're talking about a good research study, we'll control for blank, which are not part of the original design, but they could actually end up affecting the outcome, what you're measuring. Those are the confounding variables. Confounding variables. Confounding variables in this study could be what? Maybe how dry the wood is, moisture in the wood. If that affects things, you want to try to control for that, or at least measure that to account for that in the study results. Good. Do you understand control group versus not having control group? That a control group helps to reduce different biases and what it means for blinding. Know those terms or definitions too, to be able to identify if they play a role here. There's not really blinding in this example unless you, the machine I suppose is blinded to not knowing what kind of wood it is and what size flakes when it measures strength.
You can actually go in depth what exactly the definition for confounding is.
Confounding variable is a variable which influences the response. It's related to the response, but also is influenced with the explanatory variable. Connects are associated there. So if you're seeing changes in your response, And that's from manipulating changes in your explanatory. You don't know if it's the explanatory making those changes or if it's this other variable out here that also is related. And maybe it's changing too. So you can't separate the effects that you're seeing here and the change in your response of whether it's due to the explanatory or also due to that other variable. So it's mixed up. Lurking variables are confounding variables which you can't measure because you don't know them or haven't been able to control for them. And then there's this also thing called an interacting variable, which we haven't really focused on, so we're not going to be asking about that. But they play a role in studies too. All right, so they are not the primary explanatory variable of interest, but confounding variables might be recorded so that the study results can be adjusted for weight, height, what other factors might influence whatever you're measuring. Good. All right, we have an insurance policy that pays out quite a lot when the person dies, some amount if they become disabled, and we have estimates of how often those types of things, those untoward events occur. 1 out of every 1,000 people for the death rate due to this particular condition, and 2 out of 1,000 when they end up suffering from some disability. The amount paid out is what we're looking at here. That's our variable X. And we only pay out 10,000, 5,000, or nothing. But people are willing sometimes to take out these insurance policies so that if that thing happens, they would be compensated accordingly. We have some missing values. Do we understand where this first probability value comes from? That's what? 1 in 1,000. 1 in 1,000 is the rate for this supposed death that would happen. And so there's our payout that only happens 1 in 1,000 times. And what should the next value be? 2 out of 1,000, 0.002, because that's the other rate that's provided. Do I just put a 0 on that last one because I didn't talk about it? No. What does our table of probabilities need to add up to? 1, to be a legitimate probability distribution. That means 99.7% of the time, we don't pay out anything. Now, this is what kind of variable? Is it discrete or continuous? Discrete. It's got a finite number of outcomes. Even though it's amount of money paid out, which you can think of as being quantitative, it's not continuous. It only has these 3 values. So it's a discrete random variable. Is it a binomial random variable here? Binomial would be your variable X that's doing the counting. How many were successes? 1 success out of 10, 2 successes out of 10. You're counting the number of successes. The values of your X would be 0, 1, 2, 3, up to n, whatever your n is for your sample size. So it's not binomial, it's a general discrete. All right, we have our model that's complete. You had a couple on your homeworks where maybe a couple spots were missing. We told you one was twice as likely as the other, so you could figure out how to work out those probabilities to get them. There'll be some weight to these probabilities so that afterwards, if you use those probabilities in the next part, you're not going to be penalized twice if you do it wrong in part A, as long as you use those values in part B correctly. And what do we ask for in part B? What is the expected payout per year for such a policy? Expected payout. Expected value, another word for mean. Ask you to find the mean. Now, you have a section on your yellow card. Make sure you're looking over this as you're trying out those old exams for review questions, that you're kind of comfortable with where things sit on this yellow card, front page and part of the second page. And one spot down here says discrete random variables. Mean, expected value. Expected value X or mu, and here's the formula. That's what it looks like. So remember how we found the mean? There's a big basket of balls, a lot of balls in that basket, and only 1 in 1,000 of them have $10,000 on them. And 2 out of the 1,000 balls in there have 5,000 on them. And there's a whole bunch of balls with a 0. You find the mean or the expected value by taking every value times its probability. Every value that's possible gets weighted by how often it would tend to occur. I don't really need to write out that last one since it's a 0, but there it is complete. Now I get some students that still want to divide by something when you're finding a mean. Like they'll divide that total by 3 because there's 3 things they added up. But the dividing's already done. That dividing is 1 out of 1,000, 2 out of 1,000, 997 out of 1,000. The divider of 1,000 is like already there. So you just work this out, and you get what? You get 10 here, and 0. So, whoop, 20. 20 what? What are my units? Expected payout in dollars. If I didn't show my work, if I didn't include units, I'd lose a point here and a point there. And you're doing the right thing, and you just put the answer down without reading those special words. Sometimes they're bold and italicized, or when you're reading the question, circle units, symbol, so you don't drop something like that off.
Showing your work, does that include indicating the equation you use?
The equation would not have to be there for the background work. As long as I see a few things that you plug in. I mean, I can even go from that second line down to $20 pretty easily myself, but showing me a little bit of the work so I can see what numbers you plugged in. And then if you just did an algebra error, 2 plus 2 is 5 instead of 4, you might still get some credit if I saw the 2 plus 2 part that was there. It is $20 per policy, right, per person, or per year per policy, and that's what they ask for, but the units are still dollars. Symbol could be either capital E, expected value of X, that's an acceptable symbol, or the Greek letter mu, because this is a population mean, based on the model that describes the population of payout values. So I would need one of these two. So although you didn't need the formula, you do need the symbol. Not X bar, because it's not a sample. It's a model that describes the population. All right, why is it okay to say the mean is $20 here? 20 is not even a number that I ever pay out to anybody. How can that be the mean? It's what you expect to pay out on average. You may not pay out $20 to anybody. You don't. 0, 0, 0, 0, lots of zeros. Somewhere a 5,000, somewhere a 10,000. The average across all those is about 20 per person, per policy. So you guys sometimes think that you have to round your expected values up or down to a whole number because you can't have a fraction, or here it ends up being not even a value you can actually take on, but that's okay. That's the mean, the balancing point. It's what you expect on average.
This one could be in decimal.
We wouldn't want to, this is in dollars, so not decimal form. All right, now what if we charge $50 for a person to have that policy? What will be our profit then? We charge 50, we pay out on average how much? 20. Our profit would be on average 30 per policy per year. That's just thinking through the implications of here's what we expect to pay out, what should we charge, knowing certain costs for processing things, and making sure we're going to make some money in the end. Charging enough, a low enough value so people would be willing to take it out for the possibility that something might happen, but not too much, so that we will still have people taking it out. All right, I've got a clicker question for your question number 4. I'd like to see if you are able to pick out a correct interpretation. You've seen these ideas a few times. Question number 4 is looking at how long it takes a bank teller to serve a customer. Time. Service time follows a normal model. Mean of 2 minutes, give or take 0.5 minutes, a half a minute. Oh, I'm going to have A, B, C, D, E, or A, B, C, D, sorry. These are the numberings as in your page, but let's have A be this. And I'd like you to pick a correct interpretation for that 0.5 number, the standard deviation. So if you haven't read them through yet, please do so. You have seen this a few times. Standard deviation looks at how far away values are from what? Mean. All right, I'll call it in 5, 4, 3, 2. So if you were committing to one, which one would you pick? Some cases there can be more than one, but I'm asking you to at least identify one. And we'll stop. All right, there is no E. E would give you minus 10 points on the exam. All right, C and D though. There is only one, and it is C. Let's point out why the others are wrong and what features in C make it right. So very few picked A and B. In A, does that half a minute standard deviation mean that the service time for all customers is about a half a minute away from the mean? So if the mean is 2, here's 2.5, here's 1.5. Does everybody sit here or here? No. All customers are about half a minute away from the mean. They're all over here or all over here? No. It's actually what kind of model to describe the distribution. It even says it right there. It is a normal model. All right? So that's wrong. That's not telling you how far away everybody is from the mean. The average distance, so that's a good word. It's a good phrase to have. The average distance among the service times is about half a minute. That's not that bad. It's missing, though, one key idea, which is telling you how those service times vary from the mean, not from each other. Not that the service times vary from each other about half a minute apart from each other, but from the mean. So it isn't bad. It's talking about average distance of your service times, but it needs that frame of reference from the mean. So that's wrong. You could correct that one pretty easily. The average distance of the service times from the mean is roughly a half a minute. The service times vary from the mean with an average distance of half a minute. That's what the third one is saying. That is a correct statement. It's got the key ideas that you're talking about more than one service time. You're not saying the service time is half a minute away from the mean. No, the service times vary from the mean by about, roughly, approximately, any one of those words, half a minute, and then it's on average, or with an average distance. What's wrong with D? This was on your homework. It was the two researchers. You had to decide which one was giving you a right definition. We would estimate the average service time to be about half a minute away from the mean. What is the average service time? The mean of 2. Is the mean about half a minute away from the mean? No. The mean is the mean. The average is not going to be half a minute away from the average. Take out that first average. We would estimate the service times for customers to be about a half a minute away from the mean, and then add an on average at the end. That would work. But the average is not a certain distance away from the average. Average and mean are used interchangeably. And the first thing talks about a particular number is so far away from this particular number. Okay. Standard deviations give you a yardstick to know how far away values are on average from the mean. You know that if an observation were 3 standard deviations above or below the mean, that's pretty extreme in a bell curve. That would not happen very often. All right, we're going to be using the fact that we have a normal model here to work out part B. We have a model to describe how these service times vary. Their mean is 2 minutes. In fact, let me ask you this before we draw that picture. What symbol would you use to represent the 2? It's a mean, so you have 3 to choose from, but 2 primary ones. X bar or mu. This is the mean for the model that has a bell curve shape to it. Has it said anything about taking a sample or anything yet? No. This is a model that describes the population of all service times. So this is mu. And what's this number over here? This 0.5 would be represented by sigma, not S. Because it's not based on a sample, it's the model that is used to describe the population of values. When you write your big N for normal, when we draw this picture next, if I were to write the notation for my picture, I would put 2 and a 0.5 here, and that is your mean, and that is your standard deviation. If you were asked to draw the model for service time, bell curve, right? X on here could be service time. Where would it be centered at? 2. Could you put a few other values on that x-axis? I would draw about 3 tick marks equally spaced going out each side before the curve kind of comes down close to that x-axis, and these would each be a standard deviation going out. If I had a blank set of axes for you and asked you to draw the curve and label the axes, what would be the label for that y-axis? Density. It's a density function. Or there's an f of x function to draw that. We didn't show you what that f of x function looks like. It's kind of messy with an exponential and all kinds of things. But you don't need to be able to draw the height of that curve because you have a table that allows you to find areas underneath it, the different approach. All right, what do we want to find here? What is the probability if I randomly select a customer? They'll have a service time of 2.64 minutes or more. All right, so 2.64, somewhere right here. 2.64 minutes or more. Watch for those keywords. Are you going to the right or to the left? At least, at most, that you go in the right direction. That's the area I want to find, because area corresponds to probability for density curves. All right, so what do I have to do? There's probably a couple of minimal steps I'd want to see for work. You don't have to draw the picture, but I like the picture, because now I can tell you that the answer is definitely less than a half, because that's just a little area to the right of that number. It's not more than 50%. When I go to my table, I'll be likely to do the right thing with the answer I look up there. I need to see what? I can't look up 2.64 in your table A1. You've got to do what to it? Standardize it. Get a z-score. So let's do that for sure. Show that bit of work. 2.64 is being standardized. You always standardize by subtracting the mean, dividing by standard deviation, and 2.64 minus 2 over half, what do you get about? 1.28. That's your z-score. That is something I can look up in my table and find the area to the left, because that's what my table gives me. So if I look up 1.28, I will automatically see that that answer that I look up there can't be their answer here. Because 1.28 and the area to the left of that is what? 8,997. Almost 90% to the left. That 8,997 that I'm seeing is this area here, which is not the answer I wanted. What do I have to do as the final step? 1 minus. So the probability is 1 minus that. What is it? 1003, about 10%. Couple steps of the work. I would like to see a z-score so I know what number you're going to the table with, so that if you calculated everything by plugging it in correctly, but your answer came out to be 1.18 or whatever, at least you might not lose the whole thing if you just had your answer down there. And then if you looked up an answer and had to do something with it, maybe showing that part too. Because if you are off of a line in your table, oh, I can go and say, where did they get that number? Oh, they just went off a line. And again, I can maybe give you half the credit of that problem. And take it back to your picture if you drew one to make sure it makes sense. So about 10%. Watch for words at most or at least. What if I had asked you for the probability of 2.5 or more? Would you be able to do that without even really going to the table? 2.5 is exactly 1 standard deviation above the mean. When I think of 1 standard deviation, how much do you think of in between? 1 standard deviation. 68%. So what's left over? 32%. So what's the one piece over here? 16%. And I would accept that answer. If you look it up in the table, it's 1587 or something like that. Close enough. If it ends up being in a z-score that you know, a 1, 2, or 3, you may use the empirical rule for your answer. We will accept that. All right. How about part C? So we've already established that about 10% of the people take 2.64 minutes or more, right? About 10% of the people take 2.64 minutes or more. That's how likely it is to see a success, no, actually a failure, taking too long. Suppose we take a random sample of how many? 4 customers. All right, so I've got 4 customers being randomly selected. What's the probability that at most one of them will take that long to be serviced? All right, so there's 4 people. So what's the chance that the first person's going to take that long or longer? About 10%. What will be the chance that the second person does? About 10%. Right? All 4 of those people would have the same probability of taking that long or longer, about 10%. I have 4 people selected randomly, and I want the chance of at most 1. That means either 1 or fewer, none. What kind of scenario am I in here? I'm actually have moved now to a binomial problem. I've now taken a sample of 4, there's my n, and I'm counting whether or not they took 2.64 minutes or more to be serviced, success or failure, and I want to know the probability of seeing a certain number of successes, 1 or fewer. It's a binomial problem. The binomial problem where n is 4 and p turns out to be how much? About 10%, actually 10,1003 from part B. So you could use about 1003 or about 10%. And I want the probability that the number who take 2.64 minutes or more in my sample to be at most 1. At most 1 means there was either exactly 1 person or there were no one, 0. And now I've got to calculate both of those probabilities, recognizing that they come from this binomial model, where the success rate is about 10%. So that binomial formula is on your yellow card on the front page. So you don't have to try to memorize it. What do we have for the first term? We have 4 people selected, so it's 4 choose 1. I'm going to use about 10%. You would be certainly fine to keep it as 1003, but it won't change the answer that much. 10% is the success rate, and there's only 1 success. What's the failure rate then? About 90%? And if 1 person's success, then how many failures? 3. There's the first term. The second probability is a 4 choose 0. And there's nobody with a success. And there's all 4 with a failure. This problem would have more space to work out the details. There'd be some partial credit worked out. If you found only exactly 1, you might get some credit if you didn't go 1 or fewer. These are binomial coefficients here that I can do in my head. What's 4 choose 0? How many ways to take no one? 1 way, pick no one. 4 friends, how many ways to take no one to dinner? Just 1 way, don't invite anyone. 4 choose 1. How many ways to pick the 1 person that's going to go with you out of the 4? 4 choices. You don't even have to do the factorial for that at all. And then just work out the raising to power. Here's where I would do a little bit of work, showing a couple intermediate steps anyway. Because if you just have a final answer and it says show all work and there's only a final answer, you'll get no credit if there had to be work behind it to some extent. Now, if there's 90% of the table and you just have to figure out there's 10% left, I don't need to work out 1 minus 0.9 equals 10%. But when there is definitely work behind it, you need to show some of it so we can see where your numbers are coming from. It benefits you for getting partial credit if you forget to do something along the way. All right, the two probabilities. This first term should be 29, 16, and the other term, raising 0.9 to the fourth, should be 65, 61. Adding those two probabilities up gives you a pretty likely chance of seeing one or fewer, 9477. How many would you have expected out of 4? What's your expected number of people who would take 2.64 minutes or longer to be serviced? What's your expected value in a binomial? Just n times p. 4 times 10% is about 0.4 people on average. So I should see lots of zeros and I should see lots of ones. And that's why these two numbers are pretty likely. All right, little different problem there. It went from a normal to a binomial without saying binomial specifically. 4 questions done. Now we turn to confidence intervals. Random sample of 80 students, and 50 carry their books and notes in a backpack. Counting how many carry their books and notes in a backpack versus, I guess, some other way of carrying things. We are asked to compute a 90% confidence interval for the proportion of all students who do so. This sentence right here, this part of the sentence, proportion of all university students who do this, what's the symbol for that statement? I want a confidence interval for the proportion of all people who do this. That's P. Confidence interval for the true proportion or population proportion P. All right, and I want 90% confidence. And what do I have? I have a random sample of 80, and 50 said yes. 50 out of 80 was already provided for me as being 0.625. What's the right symbol for that number? That's p hat. That's the proportion in your sample. Now it asks for a 90% confidence interval. Didn't say a conservative one. So from our yellow card, it says, take your p hat, go out plus or minus z star. And then it's got written there, standard error of p hat. You need, of course, then what that is, which is also provided. Standard error is that square root of p hat, 1 minus p hat over n. So I have 3 different parts, probably be a point for each one of these to be plugged in correctly. P hat, of course, is 0.625. How about z star? Is z star 0.9? I want 90%. Where is the easiest way to find z star? Not table A1, but table A2. Table A2 is really multipliers for confidence intervals. Here they're called t stars, but your z stars are there. You use your table A2 and find your 90% level of confidence at the top, and then go down to the very bottom by the infinite row. Those are all your z stars. So you don't have to look them up the longer way from table A1. If you have one and your person next to you doesn't, maybe you can show them. 90%. Maybe you have this number in your head a little because we've used it a few times. What is my z star? 1.645. There's everything plugged in. If I plug everything in and then I do some silly calculation like forget the square root, I might lose 1 out of 3 points rather than nothing for a wrong answer at the end. The margin of error, when you work that out, 0.089, giving a confidence interval ranging from a lower bound, 53.6, to 71.4. I've written it here in proportion terms. You could also put percent as long as you convert it over with a percent sign. There's my 90% confidence interval. Question?
On the values to the left in the z-score, the confidence interval for 90% is 1.28.
All right, when you're using table A1, what is that table giving you? All the way the area to the left. You don't want the area to the left to be 90%. You want the area in the middle. So if you want 90% in the middle, what's left over in the two tails together? 10. What's left over in the one tail? 5. So you want 5% and 95% in the middle. Go to table A1 and look in the middle for 95%, and you'll find 1.645. So you have to work with that table A1 a little differently. You don't just look at 0.9 in the middle. You have to look at 0.9 being in the middle, so that means 95% is to the left. If you're using it from table A1, you need the full area to the left to be 95% to find that Z star that way. It's a lot easier from table A2. It's already done for you. Yes?
Are always going to be given the exam like these types of confidence, or are we different?
I have never, in any of the applied work I've done, been asked for an 82% confidence interval or a 97.6%. I mean, these are your common levels. 95, 90, 99. Most common. Those are what we'll ask you for. All right, there's our confidence interval. Was it okay that I did this? Were my conditions met? What are the two conditions? First, tell me about your sample. What kind of sample does it need to be? A random sample. Did it say we had a random sample? Yes, good, check. What's the other condition? I can only do Z stuff if my sample size is large enough, and that requires the check. Something like an n times p and an n times 1 minus p. And all I have is my data here. I don't have p. So I can't check n times p is at least 10. I have to use my data. N times p hat. Is it at least 10? Did I see at least 10 say yes? Yeah, how many said yes? 50 said yes. Did I have at least 10 say no? 30 said no. Those two numbers are at least 10. It was okay to do the large sample confidence interval here that we're doing, looking up a Z star. Otherwise, you'd have to go back to a binomial confidence interval, which we didn't teach you. There is such a thing, but we didn't go through that. All right, how about that next sentence? Can you fix it? Because it's wrong. It's easy. This was one way that we didn't have to spend lots of hours grading when we asked you to see if you understood what a confidence level means. The researcher wrote out this interpretation. We're even telling you it's wrong. You're not even going to have to guess whether it's right or wrong. It is wrong. And you can correct it by replacing one word. Let's see. Does it start out with the right thing? If many samples were taken, 90% of the resulting intervals are expected to contain the sample proportion. What word should be crossed out? What word should be put in? And population proportion could also be represented by what symbol? P. True proportion would work too. Yep. True proportion would be fine too. We accepted both population or true. Pardon me. That was not bad. This is interpreting the confidence level. Did my interpretation need my values I got in part A at all? No. I calculated the interval, and I am confident that somewhere between, whatever it was, 53.6 and 71.4% of all university students carry their books and notes in a backpack. It's my range of reasonable values. I'm 90% confident. But what's the probability that the interval you calculated in part A has that true proportion P in it? What's that probability? That the true proportion is in your interval you have in part A? 0 or 1. It's either not in there or it is. P is a number. You don't know what it is, but it's a number. And it doesn't change. It doesn't have a distribution or set of values you could take on. It's a single number. And that true value of P is either in that interval you just made or it's not. But you know if you were to do it over and over, getting all those different possible confidence intervals, yours is one of them, but all those different ones, 90% of those intervals would have the true proportion in. That's why you're confident about your one you're using. You're confident in the procedure, the statistical method that was used to make your interval estimate. All right, question 6 is a testing of hypotheses. In the past, the percent of all drivers who have used a seatbelt is 77%. What is believed now? That population proportion is higher. So let's look at a survey of 72 randomly selected drivers. 61 used a seatbelt. 61 out of 72. 61 out of 72 is 84%, 85%. All right. First step in putting a theory to the test is stating the theories that are going to be put to the test, how they're competing. What should always go in both H0 and HA for you on Thursday night? P. Not P hat, not X. P0 doesn't have to actually be written out. P0 is a number in this problem, but we know what that number is. We should put a P, because we're testing about the population proportion. H0 should be the status quo. It should include the null value or this P0 value. What would be the status quo if there really was no change? P should still be 77%. Now, have some students want to put that 84, 85% in here somewhere too. But that's your data. You don't need the data. You don't even have to look at that yet to state the hypotheses. H0 is that P is still 77%. What does the chief believe that he wants to put to the test? That it is greater, higher. Should I write greater than or equal to in HA? The equal only goes in H0. If you wrote H0 as less than or equal to, that would be fine. That is what you're testing. Is it more than 77% or not? But once I show that I'm more than 77%, I'm more than 76, I'm more than 75, I don't need the less than part. I need the equal part to know what to compare my data to. You can state the theories even before you look at the data. The data might be given up front, but I don't need to use it to write out the theories. I don't need to see a P0 anywhere here. It's already there. What is P0 here? 0.77. That is your null value, but it's a number that I will actually put in there. All right, you have learned 2 different tests you could do to do this particular question. You have learned a large sample z-test or a small sample binomial test. How many people did we survey? 72. That looks like it's kind of large. I certainly wouldn't want to have to do a binomial with that many, but is it large enough? So which test can we do? Can we do a z-test? Step number 2, if you were asked to complete it, would be check the conditions to see if you can do a z-test. We have a random sample of drivers, but what was the other one? It's again that n times p idea. Generally, it's n times p is at least 10, and n times 1 minus p. Now, when we did the confidence interval in question 5, we didn't have p, and we had to put in p hat. You had to look in your data. When you're doing a hypothesis test, you do know the true value of p if H0's true. And when you're doing a test, you say, let's pretend H0's true and compare our data to it. So we can assume H0's true, because that's how you do the test. Let's assume H0's true, look at our data relative to it, and decide whether it supports that H0 or we would refute it. So we use P0 here, not P hat. We check if H0 were true, would we have expected at least 10 yeses and at least 10 no's. And there's really only one of those two that I have to check, the smaller one. This would be the minimum that I would need to see checked, and that 72 times 23% is about 16 people, 16.56, and that's at least 10. You could.
That you did 20.
The number 20 is coming up here because obviously if you need at least 10 yeses and at least 10 no's, what's the total that it has to be? 20. If I gave you a sample size of only 12 or 18 or 15, you know it has to be binomial. It couldn't be a z at all because at the minimum you need at least 20. All right, so we can do the z-test, so that's what we want to do next. Calculate the test statistic and get the p-value. So you do have the z-statistic on the second page of your yellow card. Only a little bit of that second page, that top left corner. There's my large sample z statistic. There's the formula. Now I want to plug everything in. Here's where we use the data. What was p hat? 8472. And the null value that we're comparing that to is the 77%. I am bigger than 77%. But I don't just go ahead and reject H naught here because I have to see if I'm big enough. Common mistake. In the bottom, they don't use the p naught value. They would put in p hat. They would put the regular standard error down there. But this is the null standard deviation that we can use because under H naught we know what p is. Maybe top and bottom would be nice to show a little intermediate step. We're about 7.7% higher in our data relative to the yardstick of about 0496. Front cover of the exam says carry things out to about 4 places. At the very end here, when I get my z-score, I'll probably round to 2 places because that's what my table goes out to. 1.56. Anyone did it ahead of time? So draw me a picture of the p-value. And then find it too. In fact, you've had that question on the homework. What's the distribution of your test statistic if H naught's true? What's the model you use to find your p-value? Not any normal or a particular normal? Normal, 0, 1, or standard normal. What's the model for your test statistic? Z, if H naught's true. If H naught's true, I standardized the z-score correctly. I subtracted the correct mean. I divided by the exact standard deviation. So the model would be a standard normal. This is my H naught model. Put on there what you observed, 1.56. And find the p-value. Find the probability of getting what you got for your test statistic or something more extreme, assuming H naught's true. How do I know which way to shade? It is not always going to be the tail. The direction you need to shade should always match your direction of extreme in HA. It is here to the right or to the larger values. It's possible that you thought things went down and then your data comes in and it went up. Well, then you're no way going to reject H naught there and you get a huge p-value in that case. Can you look up that number now? Similar to the example we did a few questions back. I want the area to the right. You'll look up the area to the left. It's page 56 in your lecture notes, or hopefully you printed off the table from C-Tools at some point. Was it 9406? So 0594 is your p-value. You're taking the exam, you're running short on time, because maybe you tried to do one of the other questions that was supposed to be a normal model and you did it as a binomial. Took forever to work out all those probabilities or something. But you get to a testing problem. In order for you to answer the question of should you reject or fail to reject, or to say whether you have statistically significant results, you need a p-value. If you're running short on time, put down a p-value. If you don't have time to do the whole test, then use that p-value to make your decision. And I'll give you credit for the decision and the conclusion if you've done that in the right way. Now, if you say the p-value is 9406, you'll be marked wrong. But then if you say for your decision, stay with H naught, fail to reject H naught, I'll give you credit for that decision still, because that's what you would decide if your p-value was 94%. So I'll watch for consistency across that problem. All right, so we have a p-value, 0.05. And the question is asking what? Part C. Click it in. You got to get this direction right. Clicker question here, and then we'll do those true false with the clicker at the very end. Your p-value, your value of your probability is 0.0594. The question is, are you statistically significant at a 10% level? Oh, I got started. That was fast. %90 of you are going to get it right, and 10% are going to get it wrong. What is the right answer? There are 3 equivalent things, and it should be yes here. If your p-value is small, what is your decision? Stay with H naught or reject it? Reject. If your p-value is small, reject the null and say your data are statistically significant. If your p-value is small, your data is not likely under H naught to have occurred. So you reject that null. And then you can say you have significant results. If the p-value is high, then HO is your guy. You stay with H naught. And you don't have statistically significant results. I have had students write this on their exam, right at the cover. P-value is what? Less than or equal to alpha? Means what decision? Reject H naught, which means you're stat sig, statistically significant at your level alpha. If your p-value is small, reject the null, and you have statistically significant results at that level alpha. Are you significant here? Yes or no? Has to be consistent with your p-value. And the explanation, which you're asked for here, explain why. It's very easy. What's your explanation? Because our p-value of 0.0594 is less than what? 10%. I get people saying it's less than 77%. No, that's your null value. Less than alpha, less than or equal to alpha. We are significant at a 10% level. Would we be significant at a 5% level? No. We would be approaching significance. We might have enough to say maybe we should repeat the study with a larger sample size, because a larger sample size would give you what? What do you gain in terms of a testing problem with a larger sample size? More power, higher power, more likely to detect the alternative if it's true. Power of the test. All right, we have 2 short questions left. Let's try them out. This one's about probability. Maybe about 5 minutes each. All right, what do we have? Movements in a portfolio, going up or down. What does it say right at the beginning here that's an important word to know? Price movements in different time periods are, keyword, independent. Suppose they either go up or down, and the probability of going up in any particular year is 65%. So what's the probability that a particular portfolio would go down in any one year? 1 minus 35%. All right. If you know that a portfolio has risen in price 2 years in a row, went up the first year, went up the second year, you know that information, conditional on that information, what's the chance that it will go down in the third year? It's asking you, what's the probability that the portfolio will go down in the third year, given you know it went up in the first and it went up in the second. But does what happened in the third year, according to this statement here, have any dependency on what happened in the first or second? No. So probability of A given B, and they're independent, means just find the probability of A, the first part, which is how much? 0.35. You can ignore the given part because it's independent. And this would not really have a lot of work behind it. If you saw the word independent and knew that the second and first year don't matter, maybe you do 1 minus 0.65, but that I can do in the head too. All right, 0.35 because of independence. What do we have in part B? I want the probability that the portfolio moves in the same direction for 2 years. So what does that mean? It either goes up and up, year 1 and year 2 they both go up, or year 1 and year 2 they both go down. So I have this event happen if either they both go up or they both go down. What's the probability that they go up in 2 years in a row, both go up? Go up and up would happen with 0.65. What do I do? 0.65. Why can I multiply? Because they're independent. What's the probability it goes up in the first year and it goes up in the second year? When there's ands and they're independent, you can multiply. But that's not the only way this happens. It either happens this way or they go down in both years. How do I find that probability? Goes down in the first and it goes down in the second. Again, multiplying because they're independent. When you have an or, what do you do with those probabilities? You add them. Additional rule for ors or unions, multiplying for ands. So I add those two up, and I get about 50.545. Many only did it one direction. They assumed they both went up. Or they multiplied all 4 numbers, whatever. It's either one way or the other. And I'm using independence here. All right, the last 3 questions are true, false. You get to try them out with me with your clickers. You should get these right. A for sure. Short true, false questions. What 2 factors influence your margin of error? How confident you want to be, or your sample size? So what if you are 95% confident versus 90? It says here 95% confidence means whiter, as long as you're talking about the same data. Draw the picture in your head. Think of 90% in the middle, and then think of 95% in the middle. And change your answer if you said false. It's true. All you have to do is look up the multipliers or just think it through. What multiplier would I use for 95%? I would accept 2, or I would accept 1.96. What's the multiplier we just looked up a few minutes ago? There it is, wider, narrower. All right, good. I forgot to stop. All right, part B. Looking at Q1 and Q3 compared to the median. And the statement is that the median would be the midpoint. I can't start it yet because it's not done collecting. We're not doing clickers on this one. We're going to just do it. All right. Median. Is it between Q1 and Q3? Yes. Is it the midpoint? Not necessarily. Come up with any examples, some numbers. Put a bunch of 1s. Put some 2s and a 3 at the end. There's your median. There's Q1. Q3 won't. Your Q1 and your median could be the same. Your Q3 and your median could be the same. Your median won't always be the line drawn exactly halfway in your box, in a box plot. Go to any of your box plot questions. Is that line always exactly halfway in between?
Yeah.
No. Sometimes it's closer to one or the other because of the numbers that happen in between. This is false, but the last one I do want you to click it on. Last question, and then I've got a comic of the day before you go. Appropriate for Valentine's Day. I'm very curious on this one. I hope you get it right. Look at that. You need to listen. You're being influenced by your peers, which you don't get to do on the exam. But the answer here, false. You can read the first 1, 2, 3, 4, 5, 6 words, and you should stop right there. A parameter has a sampling distribution. Wrong. What has a sampling distribution? A statistic, like p hat. It does. Subtract statistic put in here instead of parameter, and you've got it correct. All right, comic of the day. Box plot, look, look, look. Can my boyfriend come along? I'm not your boyfriend. You totally are. I'm casually dating a number of people. But you spend twice as much time with me as anyone else. I'm a clear outlier. Your math is irrefutable. Face it, you're my statistically significant other. I've got a treat for you if you want one up front. Happy Valentine's Day.